So now we're going to look at these PV cycles or PV graphs. And so PV graph is simply a graph where the y-axis is the pressure and the x-axis is the volume. And it's a way to visualize. And you got to remember that we're still ultimately using the ideal gas law, PV equals nRT, as part of our analysis. But it shows the relationship between the pressure and the volume. And there's different ways that the pressure and the volume can change. And that's due to compression. So there's isothermal. That's where the temperature is held constant. So if you think of this as T as a constant, then the P is going to be nRT, which is a constant times 1 over V. And so it's going to have this isothermal, it has this kind of this 1 over X kind of relationship, like Y equals 1 over X kind of graph. There's adiabatic, where the Q is 0. That means there's no heat flowing in or out of the system. That also looks like a curve if you look at that shape. But there is a change in temperature because it doesn't imply that the change in energy is 0. It just implies that there's no heat being added or subtracted from the system. Isobaric. Iso has this word constant. So baric, like barometer, isothermal. Isobaric is about pressure. Well, so that's iso. So it's a constant pressure. Isocoric is constant volume. They'll usually tell you that, like that the volume is being held constant or the pressure is being held constant, but just in case you need to know the terminology. Isocoric is the volume is held constant. So if you see in isobaric, see the Y value, the pressure stays the same as we transition. And in isocoric, the volume stays the same, this axis. So we just move along the pressure axis and the volume stays the same. Now, notice the temperature is not really shown in the graph here, but you can, if you know the value of the pressure and the volume, and you can get a proxy for the temperature if you know the number of moles. If you don't know the number of moles, but the product of those two could be related to the temperature. Now, the other thing is if you remember from our AP Physics 1 looking at it, we sometimes looked at area under the curve, and the area was the y variable times the change in the x variable, right? And that's going to be the work. Yes, there's a negative sign, but what that means is if you look at the area under, let's say we took at this isothermal curve, we look at the area under it, it's going to give us the work, because this equation only operates when the pressure is constant. If the pressure is changing, then you technically have to use calculus, but it's just the area under that graph is going to give you the work there. And so let's take a look at going through some examples of doing that here. So calculate the work done on the gas in the closed path shown below. The curved section between R and S is semicircular. Okay, so when you have a path, there's two paths that are happening here. One, you have the area under this graph from S to R. So if I want to go from S to R, this path here, I want to think about that area. Okay, so if we think about that area, that would be, now is it positive, so we want to do work on the gas. Okay, so like an external. So because we're compressing this gas, this is positive work, right? Because the volume is decreasing, right? Because I'm going from 3 liters to 1 liter. We're shrinking that there. And so we're doing positive work. And if we look at that area, that's going to be, that's what we were talking about before. Now, when we go from R to S, we're going to do the area. So this is going to be positive work. If we do the area from R to S here, okay, that area, this green area, this is negative work. Okay, it's negative work because the gas is now expanding. So we're doing negative work on the gas. And so this is going to be a negative amount. This is going to be a positive area. This is going to be, so the red is going to be a positive area. The green is going to be a negative area. And so what we talk about is the net work, the total work is going to be this, because the green, that total area there, and you subtract this portion here, you're just going to be left with this area. So this area here is the total work, okay, when we go through the entire cycle, okay? And that's how we get positive or negative work out of these kind of systems. This is a thermodynamic cycle here. So we just look at the area of that thing, and that's going to be the total work. And it's going to be negative, and that's because the expansion, that area is greater negative, has more negative area than like the red part here that had positive area, right? And so the total work is going to be the area, and that's going to be the area, half of the area of a circle. Well, actually, it's, yeah. Well, okay, so it's a little bit tricky because you can get the area, and then we might have to do a unit conversion. So I'm going to fix it in the notes. Let's just, for simplicity, let's just say this is 10 to the 5th pascals. Actually, let me just say that this is in pascals. And then this unit here is in cubic meters. So we can just sort of not worry about the fact that it's not a circle. So it's half the area of a circle, and the radius of that circle is 1. So it's going to be pi over 2 times 1. That's going to be 1.57 joules, like that. Okay, so I'm going to fix that picture. The process carried on the opposite direction. Oh, and this should be negative. Okay, if we go in the opposite direction, we switch it. Now all the areas are flipped. It's going to be positive work undergoing from S to R, and then from R to S, it would be negative work because it'd be expanding there. And so the work done on the gas would be positive 5.7 joules. Same area. So that's why I never use the formula to determine if the work is positive or negative. I just think about it, is the gas being compressed or is it being expanded, to see if the work being done on the gas is positive or negative. Okay, let's take a look at this other process here. Find the work done, and again, I'm going to change these units to 10 to the 5th pascals and cubic meters, so we don't have to deal with the unit conversion stuff. Find the work done in each of the processes from A to B. A to B, there's no change in volume, so the work is 0. Work from A to B is 0 because the volume, there's no change, right? So the gas is not being compressed or expanded. There's no displacement, so that work is 0. From B to C, again, we want to think about the entire area from here all the way down to the x-axis. Okay, and then that work is going to be, because the gas is expanding, it's negative work. I'm going to apply force. This should say done by the gas in each of the processes. So that's going to be 5 is the height, and the width is 4. And that is going to be done, that's going to be negative. So it's going to be negative 20 joules. The work from A to D. Oh, this one has the arrows wrong. Okay, it's not a complete cycle. It's just saying like, oh, okay. And then let's talk about from here to here, A to D. Again, because it's expanding, right, it's going to be negative work. So it's going to be negative. The height of that is 2, and the width is 4. So it's negative 8 joules, because that's a rectangle there, right? Just saying 2 by 4. And then work from C to D, because there's no change in volume, it's not expanding or compressing, the work there is 0. Find the internal energy change between processes AB and BC. Okay? Find the internal energy change. So the whole idea of the internal energy change is we don't know the heat added. We know the work being done. We don't know the heat added. So we're just going to focus on knowing the temperatures if we can, right? Because we have a little bit here. Now, this one, in order to find the internal energy, I think I was supposed to give you the number of moles for monatomic gas for, we'll say 2 moles of atomic gas. So when we're going to do this, the final temperature is going to be 3/2 nRT, right? nRT final minus 3/2 nRT initial. Because remember, the internal energy is 3/2 nRT. Well, we can factor out the 3/2 nR and just get T final minus T initial. Now, how do we get the temperatures? Oh, maybe we don't actually need the temperatures. The temperatures, we're going to use this PV equals nRT. Okay. So the temperature is going to be PV over nR, right? So you can do PV. So if we're going from A to B, we're going to look at the pressure at B, the volume at B over nR, and then minus the pressure at A minus the volume at A over nR. So the nRs are going to cancel if you distribute that. So it just becomes 3/2 times the product of pressure times B times volume of B. That's going to be 5 times 3. And the minus the pressure at A is 2. The volume at A is 3 minus 6. This is going to be 9. It's going to be 27 over 2. What's that? 13.5 joules. Okay, so that's for AB. And then for BC, we do the exact same process. 3/2 pressure at C times the volume at C, which would be 5 times 7, which is 35, minus the pressure times volume here, 5 times 3, which is 15. So that's going to be 20 times 3 halves, which is 30 joules. Okay? Find the internal energy difference between states C and A. So again, we're just going to do 3 halves, and then we just do the product of the pressure at C, which is 35. And the product P times V here is going to be 6. So that's going to be, I don't know, 3 halves times 29, 43.5 joules. And you could have just added these two, honestly, because if we say from A to B, we have a change in internal energy. From B to C, we have a change. So the overall change would be the sum of those two. Find the total heat added in the ADC process. ADC process. So not technically this process, but the ADC. But again, that part doesn't really matter because we know the change in internal energy now. It's Q plus W. So the change in internal energy from between A and C is going to be 43.5 joules. Is Q plus how much work did we go from A to C was just how much work it went from A to D, because there's no work here. You're just going to add the work. A to D is -8. C to D is 0. So there's just going to be -8 here. So the Q is going to be 51.5 joules. From the information given, can you find the heat added in the process A to D? So if we look at A to D, again, we're going to do the same thing here. From A to D, though, let's see. We need to find the change in internal energy from A to D. So we got to do the 3 halves change difference in the product of PV. So it's 7 times 2 is 14. Minus 3 times 2 is 6. So it's just like we did before. And then the work done in that process we said was -8 joules. Right, we did that in part A. And so the Q is going to be positive, which is how much heat is added. This is going to be, what, 8 times 3 halves is 12. 12 plus 8 is 20. 20 joules of heat was added. Okay. Let's look at this example. A sample of gas goes through an adiabatic cycle. Adiabatic means Q equals 0. As shown in the figure, the dashed line are isothermal lines. Is work done on the gas positive or negative? So we're doing on the gas. We're squeezing the gas because the volume is decreasing, right? This is a volume pressure. The volume is decreasing. So we're squeezing the gas. So the pressure increase. Oh, so we're doing positive work on the way. Positive. Does the internal energy of the gas increase or decrease? These are called isothermal lines, and they represent increasing temperature. That's one way to think about it. So the temperature increases, which means the internal, so it increases because the temperature went up. The other way to look at it is that the internal energy is the 3 halves nRT or the 3 halves PV, however you want to think about it. And you look at the product of the pressure and volume, it's greater here than it is here. You don't have any numbers to prove that out, which is why it's not as good of a method. But you can see that because they give you the constant temperature lines here, these are higher temperatures. Why do I know they're higher temperatures? Because you move up. If the product of PV increases, then the temperature has to increase, right? Does heat flow into the gas or out of the gas? Well, let's look at this. This is Q plus W. We know that this is positive, right? And we know the work is positive, so it's a little bit unclear based on the graph, but we do know that because it's adiabatic, the Q is 0. So neither. Q equals 0 for adiabatic. Right? Just like that. Thanks for checking out this video. I hope you found it really helpful. If you'd like more support, maybe you need more multiple choice practice, maybe you just need more guidance and things like that, I have plenty of information on my website. If you look in the description below and go to www.bothellstemcoach.com, I will explain all the ways I help students be successful in their AP classes.